class, and today we're going to be talking about the forms of energy, specifically talking about the ideas of potential energy and kinetic energy. Potential energy is energy that is stored for later use. This means that this energy currently isn't doing anything, it's not causing any motion, but it can be used to cause motion in a moment. Kinetic energy is the energy of moving objects. And all things that are moving are using kinetic energy. And kinetic energy can be transferred from one thing to another. As we've seen with our collisions, a moving object can pass on that movement into something stationary by colliding with it. So that's a way of passing on the kinetic energy. There are a few types of potential energy, but we're really going to talk mostly about one. There's gravitational potential energy. There's also elastic potential energy, which we may touch on. But the other forms of potential energy are ones that usually relate to something that isn't moving but can cause more motions. So chemical and nuclear energy are both types of potential energy. For types of kinetic energy, it's anything that's moving. But you could also consider small-scale movements like thermal energy is also a form of kinetic energy. For potential gravitational energy, we're going to get a formula based on our work. Now, we're only referring to gravitational energy in this case, and in that case, we're working against gravity. So for our work formula, it's force times distance. Well, the force provided by something, by gravity, is mass times the acceleration due to gravity, or mass times 9.8. That covers the force. The distance, gravity pulls things down. So whenever we refer to a distance that is up or down, we usually call that height. So m times g times height. So this means the potential energy, PE, or you could also write it as E with a little p like that. The potential energy caused by gravitation has a simple formula of mgh. This is a simplification, and this works on the surface of the Earth, and there are many other ways for us to calculate different potential energies, but that's the one for this case, and we'll use that one a lot in this course. We can actually get the formula for kinetic energy by using our definition of work, the change in energy, and kinematics. Work is equal to the change in energy, and we can use it from kinematics. Change in energy is going to be energy final minus energy initial. Now, if we consider a situation where an object starts at rest. When an object is at rest, our initial portion has no motion because it's not moving. And no motion means no kinetic energy, or I'm going to shorten that up as KE. So that means our initial energy is 0. Now we know the work done would be the amount of force you applied over the distance that you're doing it, and that will end up equaling our final energy minus our initial energy, which we have said in this situation is 0. And as before, we know work is mass times, or force is mass times acceleration. And that might be helpful, except the motion, we always measure our motion in terms of velocity. So I'm going to need to relate my acceleration and my displacement instead to velocities. So that's how I'm going to have to do this. We know two things. One, the acceleration is the change in velocity over time, or the final velocity minus the initial velocity over time. But in this case, again, we said that our initial velocity is 0. So that means we get to throw that away. And so I'll have mass times final velocity minus 0, which just means final velocity, over time is my acceleration. And then I need to multiply by what is my displacement. Well, if I took a look at my formula for displacement, displacement is VI plus VF divided by 2 times time. That's our other formula. But again, our initial velocity is 0, so I get to throw that away. So I have VF over 2 times t. Now something I notice is I'm both multiplying and dividing by t. Those t's cancel each other out, leaving us with the fact that our final kinetic energy is going to be m2 VF times VF becomes VF squared over 2. Or the way that we generally tend to write it is we bring that over 2 as a factor of 1/2 out in front, and it's 1/2 mv squared. So we're going to be using these two formulas quite a bit. So let's put them into our big boxes so we don't remember, so we don't forget. Our gravitational potential energy is m times g times h. And our measure of the kinetic energy is 1/2 times m times velocity squared. Let's do a couple simple examples using these formulas. Determine the kinetic energy of a 0.5 kilogram football that was kicked 3.4 meters west. Well, I know my kinetic energy is 1/2 times the mass times the velocity squared. So it'd be 1/2 times our mass times this velocity squared. And we see that we get 2.89 joules. A ball has 2.89 joules of energy. Now, to remind ourselves, energy is a scalar, so we do not want to include direction. Which means for this second, question, how much energy does it have when it's kicked 3.4 meters south? The answer is the exact same, because the direction doesn't matter. It has 2.89 joules, regardless of which direction, if this ball is going 3.4 meters per second. Let's practice using our potential gravitational formula. How much gravitational potential energy does Steve have when he's hung by his ankles 13 meters above the ground? Well, the potential energy is m times g times h, or Steve's mass of 66, multiplied by the acceleration due to gravity, 9.8, times 13, because that's how high he's held, and we just get to throw that into our calculators. So we see that's 8,400 joules of potential gravitational energy. That's 8,400 joules of energy that can be turned into moving Steve. One last thing is something called the Work-Energy Theorem. The Work-Energy Theorem is about stating some of the things that we know and turning it into relations with work and energy. So we know that if there's a non-zero net force acting on an object, that object will accelerate. And we know acceleration is the rate of change of velocity. So what this means is if there's a net force, that means there's a change in velocity. And as we saw, energy, kinetic energy relates to the velocity, so this means there's a change in the kinetic energy. Now, what happens anytime we do a net force and something moves? Well, we're doing work. So this means that we could directly relate the work will become our change in kinetic energy of an object. So if something was moving quite quickly and you did work to slow it down, you've actually changed the kinetic energy because it's going slower. By determining exactly the change of the kinetic energy, you know how much work you've done. Alternately, maybe something's going slow and you push on it really hard, you do work to speed it up, you'd be able to use the amount of work you've done to find out how fast it's going. And we get to bring this into our formula. This means our work, our force times distance formula would be the same thing as determining 1/2 mv final squared, the final kinetic energy, subtracted by 1/2 mv initial squared, the initial kinetic energy. So let's use this to see what's happening here with Joe. Joe, who is 53 kilograms, accelerates from 1 meter per second using a 378 Newton force over 12 meters. Well, let's just go ahead and figure out what these are. This is my mass. He accelerates from 1 meter per second, which means this is my initial velocity. That's the force that's being used, and that's the displacement, 12 meters. What is his final velocity? That's what we're looking for. This is where the work-energy formula fits perfectly, because the work used by force times distance is going to equal our change in kinetic energy. And all we have to do is plug in our values. And it seems that his final velocity is roughly 13 meters per second. There's one more note on proportionality, and this is all about relating the velocity to your amount of energy. By taking a look at our kinetic energy formula, Ke is equal to 1/2 mv squared, we can see that our kinetic energy has a squared relationship to the velocity. And we can see that because of that square on the velocity. So if I were to say I double my velocity, what does this do to my energy? Well, double means times 2. And we have a squared relationship. So times 2 squared means I quadruple my kinetic energy. By doubling your velocity, you change that by a squared amount. It's going to be 4 times the kinetic energy. This wraps it up. Have yourself a good day.